This is Heinz Hornung speaking, CEO of Felicitas Customized Engineering. In this video, we will demonstrate the transmission line calculator of Felicitas PCBSim. The transmission line calculator is one of the three signal integrity modules of PCBSim. In order to demonstrate this, we have here opened our little example, which we have used also for the IBIS simulation. And this example shows a single integrated circuit as sender and two integrated circuits as receiver. And of course we have a bit of PCB tracks in between. The first track has 50 millimeters, the second has also 50 millimeters, the third has 25 millimeters. And from the circuit simulation we know we would like to have it with 35 ohms, the transmission line, 70 and 70 ohms. Now, what we need to do is we want to give our layout engineer exact guidelines how to dimension the lines so they will match with our circuit simulation. This can be done with the transmission line calculator. In order to launch it, I make a right mouse click on the transmission line symbol and choose the entry PCBSim. Here we go. The transmission line calculator more or less connects physical data, meaning length, width, and so on, and material data, epsilon r and losses, to electronic properties like characteristic impedance and delay time. Furthermore, it automatically calculates simulation models which can be used in the signal integrity or any other simulation within Felicitas PCBSim. So the transmission line calculator we have here, first of all, it lets us choose which type of transmission line we want to use. So we have a number of different options here. The most widely used is the standard microstrip. So, and then we have the characteristic impedance at the low end side, 35 ohms, and the delay time approximately 300 picosecond. This is coming from 50 millimeter of length. The width is currently calculated to be close to 300 micrometer. Now, if I want to know how wide a track needs to be, if I have a characteristic impedance of 50, I just key it in and it automatically adjusts the width. I go back to 35 and have a look at the layer stack here. The layer stack let me define how high is the distance between the track and the ground and how thick is the copper in this instance. If I change the height, all the electric parameters will change. The same is true for the material. We can define the epsilon r, the losses of the material, and the conductivity of the copper or any other material. And we can have it simulated without losses or with losses. Well, on the right hand side we see a diagram which shows us the losses. If I go to total losses here, we have approximately 5.4 dBs at 40 gigahertz, that is, for a line with a length of 50 millimeter. Well, this is not much. If we have a digital frequency of 1 gigahertz, we will have only a maximum frequency of approximately 10 gigahertz involved, and this would just give us 1.6 dB on losses. This is negligible. But of course, for longer lines and higher frequencies, the losses are very important. So, we have seen that the transmission line calculator gives us a very nice and easy to use means of translating electronic data and lengths into dimensions of the transmission line, and so we can give our layout engineer a very nice input on how to route the board. I will now go to losses in transmission lines. For that I open a different example. This is also shipping with Felicitas PCBSim. So, and here we have a lossy single-ended transmission line. I again open the transmission line calculator, and here we have a very long line. This is almost a meter, 950 millimeters, so a bit more than a yard. And we have as material again a standard FR4 material. And of course, if we have a look at 40 gigahertz, it will already have, well, 100 dB. So very much losses. So if I simulate this, here we go. We have a 50 ohm input impedance, and we have only 1 ohm output impedance, so we will get quite some reflections. And this is what we see here. We see the red line is the output, and it has quite a low output voltage, of course, because the resistor is so low. And the green is the left-hand side of the transmission line. It's a nice rectangle at the input, but when it comes back as a reflected wave, it's already quite round and dispersed because of the losses of this transmission line. Well, this concludes the very short demonstration of the transmission line. I want to notice or to mention that the transmission line calculator, of course, can calculate differential lines as well. And we can work with differential lines, for example, as differential clock lines and so on. Thanks for watching, and bye for now.